So now we're going to be talking about half reactions and how we balance those equations. Okay, so this is going to take quite a bit of time. The only other things we're going to talk about today are experiments 6 and 7, one of which we have data for. It's just a paper lab, so we'll talk about that in detail when we do that lab lecture. And I will go through all of those with you. But first, we need to talk about these half reactions. So, oxidation. SN2 plus goes to SN4 plus 2 electrons. Lose electrons, oxidize. Reduction. 2 Fe3 plus 2 electrons goes to 2 Fe2 plus. Gain electrons reduce. Okay, so we've got oxidation, we've got a reduction. We're going to use those to balance a redox reaction. Okay? So when we have that oxidation and reduction together, they have to work together, and we have to be able to balance them as a unit. The way that we do this, however, is at least the way I do it, is by using what we call the half reaction method. So we have oxidation and reduction. Now I'm going to walk you through this list of what the steps are, and then I'm going to show you how to apply them. I'm not going to emphasize this enough. If you do these steps in this order and you do not make any mistakes, you will always get the right answer. Now, do you always do it without making mistakes? No, of course not. You'll notice that when I do this very stepwise. So you'll see every step written down. Because if I made a mistake somewhere, I need to be able to go back through that to see where I made the mistake. Because everything that came after it is screwed up because of what I did there. So we need to be able to look at that. Can I now do this without doing it? Yeah, I can, but looking where did we go wrong is very complicated. So I don't do it that way. So what we're going to do, we're going to make two half reactions. One's an oxidation, one's a reduction. Always looking for, like, in the cases we were talking about before, tin half reaction, and then we're going to have, yes, tin and iron. So there's tin one, there's an iron. We're going to balance for anything that's not oxygen or hydrogen. So the tins, we need to make sure we have tin on both sides in the same number, and then iron, we need to have iron on both sides in the same number. Then we're going to balance for oxygen using H2O and H+. So we're going to balance for oxygen by adding H2O to whatever side doesn't have enough oxygen. Of course, when we do that, we've then screwed up the H+. So the way that we fix that is by adding H+, because we're doing these in acidic solution. Sometimes we don't, sometimes we do them in basic solution. I'll show you how to do the correction for that. So balance for oxygen using H2O. Then we balance for hydrogen using H+. We then have to make sure we have the same charge on both sides. So if not the same charge, which we actually shouldn't be, we're going to add electrons to whichever side we need to make the charge the same on both sides. It's not going to be zero. It won't be. It can't be for these reactions. So you're going to need to get used to seeing those charges in these reactions. Just like we've balanced for mass in the past, making sure that we have the same number of reactions and products in terms of atoms and things, we now need to balance for charge. Once we've done that, we need to make sure that the number of electrons that are lost in the oxidation are the same number that are gained in the reduction. So we have to make those electrons the same. So when we talk about this reaction here, I'm just going to refer back to this for a second. Notice that one of these is a 2-electron process. So SN2 plus to SN4 plus is 2 electrons. But going from Fe3 plus to Fe2 plus is only 1 electron. But we multiplied this by 2. And the reason we multiplied that by 2 is because we need to have the same number of electrons on both sides. So once we do that, then we can add the two half reactions. And of course, one of the things that we can do when we add is that if we have hydrogen in both half reactions, we can cancel any of them in common. We can also do that with H2O. We can cancel the electrons. And the electrons have to cancel. If they don't cancel, you've made a mistake, because we need to have the same number lost as our gained. So If we're in an acidic solution, not a basic solution, we've got done with all of the adding, simplification, all of that, we're going to add the same number of OH minus to both sides of the equation as we have H plus. H plus plus OH minus, that becomes H2O. And then we've taken care of that. We may need to re-cancel the net anywhere. Okay? So then we need to double check atoms and charge balance. Right, and that all sounds like mud, and I know it does. So I'm going to walk you through how these steps get used. That's where we're going. The next thing we're going to talk about is how we do this with half reaction. So we want to consider the reaction between MnO4 minus and C2O4 2 minus. So the base of that is going to be MnO4 minus and C2O4 2 minus. Go to Mn2 plus CO2. Did I know how to predict those products? No. I was told that those are products. And there are several ways that we can do that. I might just tell you, here are your products, and expect you to write those formulas. You may find this at a standard reduction percentage, in which case you would see it there. We'll talk about that when it's time. We're going to assign oxidation numbers to each species. What's oxidized, what's reduced. We're going to split our two half reactions, and then make sure that the carbon and are balanced. H2O is used to balance the O. H plus to balance the hydrogen. Make sure the charge on both sides is the same. Then we multiply, yada yada yada. That sounds great. And it's still mud. So I'm going to add a note page because we don't have a lot of space at the bottom. This doesn't really scroll that much. And when I do that, I'll be able to look at this reaction on the other side. Hold up on a different screen so that I can see what that looks like so that we can do this. Okay. And close this out. So one of my half reactions, they said, here's my system. I'm going to leave off the states, and I'll explain to you why we do that. Every half reaction is based on it being a state. We're not concerned about what those states are because we're not including things. So I'm not concerned about the states. Now, do I need to know which states they are when we go to do this standard reduction potentials? Yes, absolutely we do. It's important because the amount of energy that it takes to do it to the gas phase is different than it is to the aqueous phase. But for right now, I don't care. I care about this. And one of the things that it says is to consider the reaction between those two. That gives me that skeleton. I call it skeleton. We want to assign oxidation numbers to each species. Okay, fine. Cheat. Move this down a little bit. I'm doing that so that I can the line above and the line below. Mn connected to an Mn, and carbon connected to a carbon. Okay, that's awesome. When I look at my Mn, I see that on the product side it's a 2+, and the MnO4 on the other side, I don't know what that is, but I can use inspection to figure that out. So I know that this thing is an MnO4 minus. I know that there are oxygen, there are 4 of them. That's a -2, and that gives me -8. I know that that Mn, there's only one of them, so it's got to be something, and it's got to give me a +7. So G, that's a +7. +7, 2 plus, that's a 5 electron difference. And I have to gain those. So gain electrons reduce. Yay! Awesome. When we talk about our C2O42 minus going to CO2, I don't automatically know what either of those are. So I'm going to do that over here as well. I'm going to start with CO2 just because it's a little shorter. So CO2, I have carbon. There's one of them. I don't know what its charge is yet. Oxygen, there's 2 of them. That's -2. And this thing is net neutral, so this -2 has to go with a +2. So this one is a +2. Okay, awesome. That's cool. What about this C2O42 minus? Again, I have a carbon and oxygen. I have 2 carbons. I have 4 oxygens. That's a mess. The oxygens are -2s. That gives me a -8. And of course, the overall charge on this thing is -2. So in order to have a -2 left, I need to add a +6 to that, right? So that needs to be a +6 right there. But there are 2 of them, so each one of them has to be a +3. So we go from +3 to +2. We have oh my lord, I can't do math. Isn't this fun? I've already made a mistake. This is great. And so when I did my CO2, I looked at my carbon, I said that was +2, and I said that's because oxygen is -2, so that's a -2. This is not a -2. This is a -4 because there are 2 of those. And that means that that carbon, since there's only one of them, has to be a +4. So this charge, or the oxidation state, has to be a +4. So the CO2 has to be a +4. And of course, I can verify that I did the math right on the other one. Yay. So 4 times -2 does give me -8. Adding the +6 to the -8 gives me -2. Taking that 6, dividing it by 2 gives me a +3. So we go from 3 to 4. I have gone up in charge 1, so that's a 1 electron process, and I lose electrons oxidize. So there's that. Now, I will comment, you may notice that it's always gain electron reduce in capital letters and lose electrons oxidize are in lowercase letters. There's no reason that I do that. I just noticed that I do. I don't understand why, but that's a thing. I don't think it matters. It's just I don't want you to think that there's some purpose for it when there is no purpose. So I know that this is my process that I'm looking at here. Cool, awesome. I have that. Great. Now, the next thing that I'm supposed to do, what's oxidized, what's reduced, got that. Write down your 2 half reactions. Okay, so right now, I have MnO4 minus going to Mn2 plus. I also have C2O4 2 minus going to CO2. And notice these are 2 completely different half reactions that I've written in this same space. We don't have a lot of extra room here. It's not ideal, but we'll get to that. I'll erase stuff if I have to. That's my first step. Now, the next thing I need to do is to verify that I have the same number of everything that's not oxygen or hydrogen on both sides. That's the next thing. So do I have the same number of MNs? Yeah, I have 1 MN as a reactant, 1 as a product, so that one is fine. So I'm going to write MnC, and MnO4 minus goes to Mn2 plus. Now, I told you that this was going to get repetitive when I do this. It does, because every time I write down a step, I write down the result of that reaction showing what I changed from the step before to this step. Okay. Nothing changed there, so I didn't have to write it down again. I don't have to, but I don't like to have to look way above, so I like to carry it on. When we talk about the carbon, we're looking at 2 carbons on this side and 1 carbon on that side. So I'm going to have to multiply that by 2. And I now have 2 carbons on both sides. But I didn't want to do it like that, right? I didn't want to put it right there. So C2O4 2 minus goes to CO2 with a 2 in front of it. So I want to show how I change that reaction in between the two so that if I make a mistake, I know where it happened. Okay, so that's my MN and my C line. I'm dealing with the chart or the mass balance on both of those. The next thing I'm supposed to do is O with H2O. So I have four oxygens in my reactant side over here. So MnO4 minus, there's no oxygen in that line. So I'm going to take this as MnO4 minus, goes to Mn2 plus 4H2O. So now I have the same number of oxygens on both sides. So that's that one. Now, when I look at this one, and I'm going to go ahead and write it down again. I have 4 oxygens on my reactant side. I also have 4 on my product side. So we need to make no change there. Okay, that's good the way it is. So that's O with H2O. Now let's talk about H with H plus. So looking at this half reaction, the Mn1, I notice that I have 8 hydrogens on the product side, and I have no hydrogens on the reactant side. I'm going to take and add 8H plus MnO4 minus goes to Mn2 plus 4H2O. Notice I didn't leave myself enough room. These take a lot of space. Would have been better off if I'd used the whole width, but I did some math over there. Erase and move and all that stuff. So I'm just trying to make it so that it's all on the product side. Not always that great, but there you go. We're going to do, and of course, I have no hydrogens in this C2. 2 minus going to 2, so that one is good as it is. Oh my god. Okay. Now I need to make sure that I've got charge, balance for charge. So I'm going to write that as charge. And I look at this, and on my reactant side, we're talking about this, my reactant side, I have 8 plus and 1 minus, which gives me a total of plus 7. Okay. On my product side, I have 2 plus. So there's a 5 electron difference there, which I actually already identified. So there's a 5 electron difference there. And where I need to add those electrons is where I have more positive charge. So what's going to happen is I'm going to take that 8H plus 5E minus plus an MnO4 minus going to Mn2 plus 4H2O. And of course, we identified before that it was a 5 electron process. And we said gain electrons reduced, and they're on the reactant side. So that was a gain. Chaos. Let's look at this other one. It's C2O42 minus goes to 2CO2. So my reactant side, we have a 2 minus charge. And product side, I have no charge. So I'm going to go C2O42 minus goes to 2CO2 plus 2 electrons. And now I have a -2 charge on both sides. Okay, cool. That's awesome. Now I need to make the number of electrons the same. I have a 5 electron process on the Mn side, and I have a 2 electron process on the C2O42 minus. The only way I can get those to be even is if I cross multiply. So I need to multiply this one by 5 and this one by 2. Okay. Okay. 16H plus 10E minus plus 2MnO4 minus goes to 2Mn2 plus 8H2O. So I have to multiply everything in that half reaction by that 2. Okay. We have to do the same thing down here. So I have 5C2O4 2 minus going to 10CO2 plus 10 electrons. 10 electrons in both of them. That's awesome. Because now I need to add and simplify. Let me give myself a little bit of space. So I'm going to add, and I'm going to stop breaking this up. So when I look at these two half reactions, I can see that there's 10 electrons as products here, 10 electrons as reactants there. So they're common. We cancel that. That's exactly what should happen. Their electrons should disappear. I don't have any H plus in this half reaction. I don't have any H2O in this half reaction. So there's nothing else that I can cancel in doing this. So now I'm just going to be looking at adding them together. So 16H plus 2MnO4 minus plus 5C2O4 2 minus. Remember, we need all of the reactants on that one side. And that gives me my product. 10CO2 plus 2Mn2 plus 8H2O. Okay. And that's the final equation that I'm looking at. Now, I'm still in acidic solution, so I don't need to make any corrections for that. But I do want to check, did I get this right? So H, M, N, O, C, and then charge. So I see 16H plus in my reactants, so I write 16. And I always do all of the reactants and then do the products because I don't want to influence my counts. So my Mn, I have 2 Mn. I have 8 oxygens there and 20 in the carbon species. So that's total 28. I have 10 carbons and my net charge 16 minus 2 from that 2 minus 10, and that's equal to 6. No, actually it's not. I can't do that. 4? I think that's 4. Don't quote me on that. My math is really bad. I have a calculator. Let me make sure I got that right. So 16 minus 2 minus 10 is 4. Okay, awesome. I can do that. Sort of. On the other side, we are looking at 8 H2O, which gives me 16 hydrogens. I have 2 Mn. I have 20 oxygens from the CO2 and 8 from the H2O, so that's 28. I have 10 carbons on that CO2, and then I have a 2 plus charge, and there are 2 of them, which gives me a total. So my charge is the same on both sides. And all of my atoms are equal. So I'm done. I have not made any mistakes, and that's my answer. Okay. Now, do I need to leave this here? No, I don't, but I'm going to go ahead and leave it for you guys. So that's how I go through it. It is a very stepwise process. And notice that I labeled each step that I did. I do that to make sure that I got them all and to make sure that I haven't missed anything and that I haven't made any mistakes. Okay. So that's my process. Now, I'm going to take a break at this point. We're going to come back and do a whole bunch more of these examples. And we're going to do a bunch here, and then we're going to do a bunch for the lab. It is really important that you know how to balance half reactions. Now, I'm going to skip ahead for a second, and then I'm going to come back, I promise. And I'll show you acid and base. But I want to mention to you that there is another method that you can use to balance redox reactions, and that's using that oxidation number change method. And it really is the same as what we've done before. Okay. So exactly what we talked about in the process previously. But we don't write it as like separate steps. We just do everything in one line. I find that for me, this is very confusing and very difficult to work with. Are you allowed to do this? Absolutely. Is there any problem if you do it this way? No, of course not. I have difficulty walking through this, even if somebody else has done it. So I will warn you, if you're asking me questions about it, it's going to take me a minute to look at it. I know that this can be done. I can walk through the logic on it, but I'm not very good at doing it myself. So you will notice that when we do this, when we talk about this, they have put those oxidation numbers above each of these things. Okay. So that is common for us to do. So if we're asking about oxidation numbers and I ask you what it is for all of these species, we want to label that above that thing. It's not a real charge. That's not what it is. And it needs to not be included like it is a charge. It needs to be clearly above what we're talking about. Okay. So now that I've said that there is that, there, I do not specifically work any problems in that fashion. I find that when I do, when I have tried it in the past, I've ended up confusing everyone in my attempts to do so. So I'm going to go with what I think is the more systematic method, the one that is harder to screw up. And that's what I'm going to show you. Now, if you want to watch YouTube and do it the other way, go ahead. I don't care. It's entirely up to you. I do think that there is one question on the final that says balance it using this method. I don't care. Just balance it. I will take care of it. You know, auto grading might not like it, but I can go back and do that. Okay. So there you go. We're going to come back here in a little bit and we're going to do a bunch more examples of balancing. And yeah, I'm going to take a break here. Talk to you soon, guys.